Hello, my name is Ju Jung. I present our paper titled SeaCache, Spectral-Evolution-Aware Cache for Accelerating Diffusion Models. Diffusion models generate high-quality images and videos through an iterative denoising process. However, this iterative process is also the main computational bottleneck. At every time step, the denoising network has to be executed again. As a result, diffusion inference is slow. To address this issue, diffusion caching exploits the similarity between adjacent time steps. In many cases, feature maps from adjacent time steps are highly similar. So instead of computing all features at every time step, we can reuse the output feature computed at the previous time step. This allows us to skip computation while preserving generation quality. For caching, we want to skip computation when the alpha feature will be similar to the previous one. However, the output is not available unless we run the denoiser, so we estimate output similarity from input similarity. Most previous caching methods mainly focus on how to estimate this input to output similarity relationship. Specifically, diffusion caching measures the distance between input feature maps. If the input distance between time steps is large, it means the current feature has changed significantly, so we fully compute the current output. On the other hand, if the distance is small, the current feature is considered redundant. In that case, we skip the computation. A straightforward approach is to directly measure the distance between raw input feature maps. The problem is that raw distance applies the same criterion at every time step, but during the denoising process, the meaning of feature changes can vary across time steps. Our motivation comes from the spectral evolution of diffusion generation. During denoising, content evolves from low frequency structure to high frequency details. Therefore, the important frequency range changes over time steps. This suggests that feature distance should focus on the components that actually reflect meaningful content evolution at each time step. At early time steps, informative content is focused around lower frequency components. As denoising progresses, the content-relevant frequency range gradually expands. Therefore, caching distance should focus on the informative frequency range. To capture these content-relevant components, we introduce a time-step filter that follows this spectral evolution. This slide shows a simple visualization of our Spectral-Evolution-Aware filter. At early time steps, the C filter mainly emphasizes low-frequency components. As denoising progresses, it gradually considers a broader frequency range. In this way, the filter follows the spectral evolution that we want for caching. Compared to previous caching schemes, SeaCache has only one simple step. Previous methods directly compute the input feature distance. In contrast, SeaCache first filters the features using the C filter and then measures the distance. Thus, the overall caching pipeline is simple, while the distance becomes much more aligned with actual content evolution. To verify the effect of C filtering, we first perform an oracle test. In standard caching, the cache decision is made based on input distance because the output is not available unless we run the model. In the oracle test, however, we use output distance for caching. Of course, this is not practical in real inference because it requires computing the output first, but it allows us to isolate the effect of spectral filtering. The result shows that using C-filtered output distance clearly outperforms using raw output distance. This indicates that C-filtered output better tracks the full computation trajectory. Now let's look at qualitative results for video generation. Compared to previous caching methods, SeaCache produces a much closer to the original full computational output. We observe similar improvements in image generation. In the first row, SeaCache better follows only a white background image. In the second row, SeaCache generates 7 stars matching the original generation. The quantitative results further support our findings. For both image and video generation, SeaCache achieves higher quality with lower latency compared to previous caching methods. To summarize, SeaCache is architecture agnostic and sample agnostic. It is also compatible with other acceleration techniques such as quantization, fast attention, and other caching methods. Finally, SeaCache is negligible overhead and requires only one hyperparameter, the caching threshold. In conclusion, SeaCache accelerates diffusion models by measuring content evolution in a spectrally aligned space. For details, please see our paper. Thank you for listening.